In this lesson, we're going to see the effects that a magnetic field has on a wire when the wire has current running through it. Now, when a wire has current running through it, it has moving charge. If charge is moving and it is in the presence of a magnetic field, you get QV cross B, so you get a force on the charged particles that are moving. Well, let's take a look at the situation that we're considering on this page of notes. Well, we have our three regions of B field, so we're going to have B equals 0 off to the left and off to the right, and we have a uniform B field in the middle. I have the B field in this discussion coming out of the paper. So, uniform B field coming out of the paper, and we have conventional current, so anytime you're going to be looking at the magnetic force, we'll be always talking about conventional current and reversing our thumb direction if it's electron current. But we are told to consider the conventional current coming in from the left, running through the bottom wire, wrapping around and running to the left through the top wire. And we're asked to consider the magnetic force. Well, to get the equation for the magnetic force is actually quite easy. We know that the magnetic force on each of the Q's that is moving is QV cross B. So that's my bracketed term that I have here, right? QV cross B. Well, we have to count up all the Q's. How many Q's are moving in that bottom wire, for example? Well, the number of Q's that are moving is given by the number density of conduction band electrons, so the number of Q's per volume, and where the volume is based on the cross-sectional area of the wires. That A is the cross-sectional area, and L, as I have highlighted, is the length of the wire that sees the B field. So it is very easy to see how QV cross B becomes IL cross B. If we go back and remember our Chapter 28 current and resistance equation, and please write this into your notes. I equals Q for each charge carrier, script dN, the number of charge carriers per volume, cross-sectional area, times drift velocity, QNav. Remember, I equals QNav. Well, we have QNav. We have Q, we have the N, we have the cross-sectional area, we have the velocity. So that is the current. So there is our I. We still have the L in there that goes with the length where the current length of the wire the current is flowing through. And of course we have our B field. So you will not be responsible for this derivation. However, you absolutely need to immediately know that F equals QV cross B for an individual Q, or that F equals IL cross B for a wire. Well, let's do our right-hand rule and get our thumb directions for the magnetic force for the example that we're given. Well, in the example that we're given, we have conventional current, and you'll always be using conventional current to get your magnetic force directions. We do IL cross B, and please take a moment to see that you definitely have your thumb pointing down when you do IL cross B, where B is coming out of the paper. Right-hand rule, you have to contort a little bit to do that, thumb down. For the top portion, right-hand rule, right hand, so put down your pen if you're right-handed. Right-hand rule, IL cross B, thumb up. So in the situation presented to you, these two wires will push apart. So you get a deflection, you get a bulge in the wires in the middle based on the wires pushing apart. So the only other thing I want you to now consider, and we'll talk about the answer in class, is can you imagine or come up with a situation where the wires would not push apart, where they would actually pull together? Think about things like changing current directions, changing direction of magnetic field. So I want you to consider what you would have to do. How would you change this problem to get the magnetic force on the bottom wire going up and the magnetic force on the top wire going down? So that is part of your homework for this page of notes. And we will talk about in class how you would have to change currents or B field directions to get that situation to occur.